Hi, everybody. So today I want to talk about series. This is section 10.3. And the idea here is we're going to add up the terms of an infinite sequence. So we're going to take our sequence, which is a bunch of numbers, and then we're going to add them all together, and we're going to see where that goes. So the idea is that sometimes this ends up being a nice finite number, and sometimes this ends up being an infinite number. And so you can sort of see what's going on. Other times it sort of bounces between two numbers, and so it's divergent in that sense as well. And so you can kind of see how we're going here. So a series is going to look something like this, and we talked about these last time as well, just how to calculate the sum of an infinite series. Well, you basically, to figure out that number, you're going to find the sequence of partial sums where you add from 1 up to n, and then take the limit of that sequence of partial sums as n goes to infinity. And the idea here will be, can I find a formula for Sn that allows me to then take the limit of this thing as n goes to infinity? And the formula should just involve n. It's not going to involve a sum of a bunch of stuff. It's going to just be something in terms of n. And that's the goal. That's the ultimate goal out of all of this. Because if I just have a bunch of stuff and I'm adding them all together, well, I'm just adding more terms. So how do I know where those sort of sum of the rest of those terms are going to go as well? So that's the trick. All right. So we're going to look at a couple of cases. First, the geometric series is the first specific case that we want to look at. It's the sum of a geometric sequence, and the geometric sequence is the product of c, a constant, times powers of an r, a number. So I'm looking at the sum from 0 to infinity of c times r to the k. You'll notice this sequence, or the series, has a sequence that starts at k equals 0. And this is on purpose. There's sort of a nice way to analyze these things. It gives me the ability to say that I know the first term is just c, or c times 1, because r to 0 is just 1. So this is an on-purpose thing. It helps with the analysis of this thing. I could still start at 1. I just have to do a little bit more beyond what an analysis we're going to do. Okay. So it does start at 0. That is not a mistake. That actually should start at 0. This is a divergent sequence if the absolute value of r is big, and in fact bigger than or equal to 1. So if this thing is bigger than or equal to 1, you're going to diverge, because you're getting more terms that have bigger numbers, or at least the same or bigger numbers, and you're adding them all together. That gives me a bigger number as I'm adding. And so what I get here is an infinite value in the end. It just ends up being the same, or it bounces between 2 if r is -1. It bounces between positive and negative c, so it goes sort of c, then it goes to 0, then it goes c, then it goes 0, c, 0, c, 0, c, 0. So you're adding c minus c, c minus c. So far, r bigger than or equal to 1 is this divergent sequence. It's not going to go anywhere. It is convergent, on the other hand, if r is less than 1, absolute value of r is less than 1. And so you can sort of say, well, if r is 0, it works, right? So that's great. So yeah, I can sort of do that. R equals 0. Well, the sum of this thing is just going to be c times 0 to any power. Well, c times 0 to any power is just 0. So this is just sort of a kind of dumb case, right? So we don't need to think about that case beyond there. What about if r is not 0, but it's less than 1 in absolute value, Okay. So we need to do a little bit of thinking here, but if I write out a couple of terms here, the first term of this will be c, and then I'll get c times r, and then I'll get c times r squared, and so on. Well, notice every single term in this sequence will have a c in it. So inside of this sum, I can factor a c out of all of the terms. And so I can just take this as c times 1 plus r squared plus so on. So I really don't need to think about that constant c when I'm doing the analysis of this summation. In particular, I really don't want to worry about that c. Let's add up the terms r to the k for k equals 0 to n and see if we can figure out the analysis for that. Then once I do that, then I can multiply all of that by c, and that gives me my sum of this sequence c times r to the k. Okay, so let's talk about this partial sum. So this is a partial sum. Its Sn is the sum from 0 to n of r to the k. So what is this? So we'll decode the notation a little bit. So this is just r to the 0, which is 1, plus r squared, plus r to the 3rd, plus r to the 4th, and so on, out till r to the nth power. Okay. So to try to get a handle on this thing, it turns out we want to look at a polynomial. And the polynomial we want to look at replaces all those r's with x's, just so we're more comfortable with it, is this polynomial. So we're basically looking at x to the n, so from the largest power down, x to the n minus 1, down to x squared plus x plus 1. So I want to think about that polynomial a little bit. That's the one I want to think about. This is one of those instances where someone sat in their office for hours and hours and hours and days and months or weeks or whatever, and figured this out. They said, oh, here's the trick. And so now when we show you this trick, it's basically, it looks like magic. It's kind of like, we're going to pull this out of a hat and look, isn't that great? It's amazing. But I want you to know that somebody spent a lot of time on this, so don't feel bad if it just sort of doesn't click right away. Take some time with it to see sort of where it comes from. So we're looking at this polynomial. It's x to the n, or 1 plus x squared, and so on. And then we're going to say, okay, so that's great. What is that? Well, let's start small. So 1 plus x. Well, that's just x squared minus 1 over x minus 1. You know, if I factor x squared minus 1, I get x plus 1, x minus 1. And so if I divide by x minus 1 on both sides, I get that division is x plus 1. Okay, so that's something. So the trick is this. Let's multiply each one of these partial sums by x minus 1 and see what happens. Okay, so let me repeat that. I want to take each one of the partial sums up to n and multiply each of those by x minus 1 and see what happens. Okay, so what do I get? Well, what's great here is I can multiply these together and see what happens pretty easily. I multiply x minus 1 times x squared. I get x cubed minus x squared. Multiply x minus 1 times x, I get plus x squared minus x. Multiply x minus 1 times 1, and I get plus x minus 1. What happens is what's called like a telescoping behavior. The middle terms all come in pairs, a positive and a negative with the same power of x. And so what I'm left with is just, in this case, x to the 3rd minus 1. And so I get x to the 3rd minus 1. This also happens for x to the 4th, or sort of the sum 1 plus x squared plus x cubed times x minus 1. Again, I can multiply this through. I get x to the 4th minus x to the 3rd plus x to the 3rd minus x squared plus x squared minus x plus x minus 1. All of the middle terms come in pairs, and I'm left with x to the 4th minus 1. And this will be true no matter how many terms I take. So in particular, if I have 1 plus x squared up to x to the n, multiply that by x minus 1, and I get x to the n plus 1 minus 1. So again, it's this telescoping behavior. I sort of get x to the n and minus x to the n plus 1 minus x to the n plus x to the n minus x to the n plus 1, x to the n minus 1, and so on, and so forth, so on and so forth, until I end up with just x to the n plus 1 and minus 1, because all the middle terms cancel. So this is great because, check it out. That means this sum, the sum I'm interested in, 1 plus x squared plus all the way out to x to the n, is the quotient of x to the n plus 1 minus 1 over x minus 1. And what does that really mean for us? That means if I plug r in for x, the partial sum from 0 to n of r to the k is going to be r to the n plus 1 minus 1 over r minus 1. And I can do this for any partial sum that I could possibly want. So this is great. So what are we going to do here? We now take the limit. So if I take the limit as n goes to infinity of this thing, if r is too big, if r is bigger than 1, or I should say an absolute value of r is bigger than 1, this thing on top is going to go to infinity, because you've got this r to the n plus 1 term, and it's got a big power, and it's a big number. So that big number with a big power gets really big, and it might alternate between positive and negative, but it's still in magnitude getting bigger and bigger and bigger and bigger. So this thing is going to be infinite. It's going to be a divergent sequence. On the other hand, if we have a small r value, so absolute value of r is less than 1, r to the n plus 1, that's a fraction, a smaller than 1 fraction, to a big power. And that gets smaller and smaller and smaller the bigger the power is. So what I get is that top thing goes to 0 minus 1 over r minus 1. And so I get negative 1 over r minus 1. And I want to rewrite that as positive 1 over 1 minus r. And the reason I want to rewrite it as that, and you'll notice, how did I do that? I sort of factor in a minus 1 out of the denominator and cancel with the numerator, or take the numerator minus 1 and multiply it through the bottom. It gives me 1 minus r. And so that sort of works out. And the reason I do that, so why would I do that, is that r is less than 1. The absolute value of r is less than 1. So this number down here, if it's positive, if r is positive, this becomes a positive number. And if it's negative, it also becomes a positive number. So what we're getting here is going to be something that's positive. And that's going to make a lot of sense to me, because I have a bunch of things that are added together that are positive. And so I'm going to get a positive number out of that. Or I get a bunch of things that are alternating from positive to negative, but it starts with 1 and everything else is smaller than that. So it's still going to be a positive number when I do this subtraction. And so in the end down here, that should be a positive number, which we agree that's fine. Okay, so let's sort of see what we get here. So in general, this infinite series with r to the k will converge to c times 1 over 1 minus r, if absolute value of r is less than 1, and it diverges to the absolute value of r, or diverges if the absolute value of r is bigger than 1, bigger than or equal to 1. So we have a divergent sequence or a convergent sequence, and I know where it converges. All right. So I want to do kind of 2 examples here, maybe 3, with this stuff. So the first one I want to look at is this one that I've given you. So I've got this infinite sum from 0 to infinity of 4 times 3/5 to the k. Okay, so what am I going to do here? Well, I can pull the 4 outside of this and ignore it for a bit. So whatever I get from my infinite series here, I just multiply that by 4 in the end, and it gives me what I want. So I've got 3/5 to the k. 3/5 is less than 1. And in particular, the absolute value of 3/5 is less than 1. So this thing should converge. And it will converge to 4 and then 1 over 1 minus r. So I get 1 over 1 minus 3/5. 1 minus 3/5 is 2/5. This is 4 times 1 over 2/5. And 1 over 2/5 is 5/2. So this is just going to be 4 times 5/2, which is just 10. So this infinite sum, the sum of all of these numbers, 4 times 3/5 to the k for k from 0 to infinity, is just 10. And so that's how that's going to work out for us. Okay. And I have that next part here. So you can sort of see I'm able to just apply this rule because I know it's convergent. I have to be really, really careful here, because if it's convergent, it works. And if it's not convergent, I can still go through and plug stuff into that formula. Unfortunately, that formula is not valid for numbers that have an absolute value bigger than 1. So in particular, if that was 5/3, 5/3 is bigger than 1. So the absolute value of 5/3 is bigger than 1. And so that's going to basically say this is not going to be convergent. This is divergent. And if you did go through and plug this through the formula, you would be surprised, because you would get something negative out of adding a bunch of positive things together. And so you would say, shoot, something's bad here. That's a big red flag that you should pay attention to. Don't worry about it. It's wrong. You definitely are right to think that's a red flag, and it just pay attention to it and say, oh, I see. I screwed something up here. And that's how it works out. All right. So this one is divergent, and I don't have to do anything more beyond that to say that it's divergent. The next example I want to give is actually, it's a joke that I tell a lot of my undergraduate classes, and it is this: it's how many mathematicians does it take to screw in a light bulb? The answer is it takes infinitely many. The first mathematician comes over and screws the light bulb in halfway. The next one comes over and screws it in a quarter of the way. Then the next one comes in and screws it in an eighth of the way, then a 16th of the way, a 32nd of the way, and so on forever. And eventually the light bulb gets screwed in once. So we can look at this. So what this is really doing here is I'm adding powers of 1/2, because half of the way in, plus a quarter of the way in, plus an eighth of the way in, plus a 16th of the way in, and so on, right? And I'm taking the sum from 1 to infinity. Now, this is where we sort of have to do a little bit of analysis. This is not starting in the right place. So there's two things I could do here. Either I could make this start in the right place, or I could add the missing term in. So notice I'm missing the k = 0 term in this sum. So I could add in a 1/2 to the 0. And then in the end, I just have to subtract that 1/2 to the 0 off. Okay, so I'm adding 1 to this sequence, this series. And so I'm looking at the actual series k = 0 to infinity, 1/2 to the k. According to our formula here, this is just 1 over 1 minus 1/2. And 1 minus 1/2 is 1/2. So this is 1 over 1/2, which is just 2. But I added 1 to it. And so screwing in the light bulb, I've screwed it in once because I've got twice, but I have to subtract off that 1/2 to the 0 term again, right? And so that works out. Cool. So the other thing that I want to mention here, I could also have written this as the sum from 0 to infinity, or I guess I should say from 1 to infinity, of 1/2 to the k is equal to the sum from 0 to infinity of 1/2 to the k minus the sum from 0 to 0 of 1/2 to the k. So there's sort of like one term in that second summation. And this will work for anything that I want. So I could start this summation right in the middle, and I could just sort of subtract off the bottom terms because I don't need those and work from there. So I could look at something like the sum from 15 to infinity of 1/2 to the k. It's going to be the sum from 0 to infinity of 1/2 to the k minus the sum, and I have to be careful here, from 0 to 14 of 1/2 to the k. So I want to leave the 15th term in the sum, but I want to take out all the terms before the 15th term. And so then I can do that. Now this, I'm going to calculate using the other formula, the partial sum formula that we had, where the numerator of this is r to the k plus 1 minus 1 divided by r minus 1. And so that r to the k plus 1, n plus 1, I should say, the n is 14 here. So it's going to be r to the 15th minus 1 over r minus 1. And then I know this one is just going to be 2. So I get 2 minus whatever that term is. So that's going to give me what I need. Okay. The other thing that I could do is I could re-index the summation. So if I had something like k equals, say, 15 to infinity, 1/2 to the k, I want to re-index this so that L starts at 0 when k is 15. So what that means is that k should be L plus 15. So the starting of L is 15 less than the starting of k. So what does that do? Then I plug this k into each term here, or this, and then I replace that k with an L equals 0. So I'm going to end up with the sum L is 0 to infinity. And notice, since it's infinity on the top, I don't do anything to the top. If the top was finite, I would again subtract 15 from the top of this as well. So infinity minus 15 on top, which is infinity still. And then I have 1/2 raised to the L plus 15. And now you look at this and you say, okay, so what that really means is this is the infinite sum from 0 to infinity of 1/2 to the L times 1/2 to the 15th. This 1/2 to the 15th is a constant. It can pull in front of my sum. And now I just sort of evaluate the sum like I would the infinite sum from 0 to infinity. And so I get 1/2 to the 15th, and the sum L equals 0 to infinity of 1/2 to the L. So this is just 2, right? So this last term here just goes to 2. We calculated that. Times 1/2 to the 15th is just 1/2 to the 14th power. It's 1/2 to the 14th power. So that's what we get out of our sum from 15 to infinity rather than from 0 to infinity. So I subtract off a bunch of stuff. I don't get 2 anymore. I get this other thing. So I lose a lot of terms there, and that's kind of what we would expect. Okay. The next type of series that I want to talk about are telescoping series. And this is really why we do this thing with the polynomial before this, is we look at this telescoping behavior. So the telescoping series basically is exactly what it sounds like. You have an endpoint on the front and an endpoint at the back. All the terms in the middle have pair terms that they subtract away. So essentially all the middle terms go to 0, and I'm left with 2 terms, one on the left and one on the right. Okay. And we can see this behavior by plugging in some numbers here. So I've got cosine of 1 over k minus cosine of 1 over k plus 1. What does it give me? It gives me cosine of 1 over 1 minus cosine of 1 over 2. So that's my first partial sum. My second partial sum says take that and add what I get when I plug in 2. So this is going to be S2. I get cosine of 1/2 minus cosine of 1/3. And then I get plus cosine of 1/3 minus cosine of 1/4, plus cosine of 1/4 minus cosine of 1/5. So all the middle terms will cross out. I'm left with just the outside 2 terms. So here Sn, I've got this sort of starting point of cosine of 1. All the middle terms are gone, and I'm left with cosine of 1 over n plus 1. As n goes to infinity, 1 over n plus 1 goes to 0. So I'm left with cosine of 0. So this sum will be cosine of 1 minus cosine of 0. And cosine of 0 is 1. So this is just cosine of 1 minus 1. So those telescoping series, you're looking for those middle terms to cancel. And so then you can sort of see this thing collapses in, kind of like an accordion or a telescope, I guess. And then you have the end points there. So you have a cosine of 1 and a cosine of the last term. Okay. So be on the lookout for those as well as you're going through the series here. And then finally, I want to talk about some properties. So properties of these series, they again mirror what we do for properties for limits. If I have a constant inside of a sum, I can break that constant in front. And this is, again, this maybe mirrors what you do for an integral more than even a limit. So the integral, if I have an integral of a constant times a function, I take that constant in front of the integral, right? So I can pull that constant out. Well, the same is true here. I can pull that constant outside and the sum converges to a, so I just get CA. On the other hand, if this thing is divergent, no number I can multiply except for maybe 0 would make this converge. So if I multiply by 0, it converges to 0. But if I multiply by anything else, this still diverges. So it doesn't matter. It's not going to go anywhere nice. All right. And then if I have two sequences that converge, say a sub k converges to a, the sum of b sub k converges to b, then the sum of the sum or difference of those two, so a sub k plus b sub k or a sub k minus b sub k, will also converge to a plus b or a minus b, capital A minus b, capital A plus b. Okay, so this is, again, the integral. If I integrate the sum of two things, I can integrate each of those things separately and then add the integral that I get at the end, or subtract the integral that I get at the end. Okay. The fourth one here is a little different. It's a little different than what we would see for an integral. I have a divergent sequence. So a sub k, the sum of the a sub k is not finite. It's a divergent sequence. But the b sub k is a convergent sequence. The sum of the sum or difference of these things is still divergent. So it still does not converge to anything nice, even though we're sort of maybe taking some stuff away from this divergent sequence. We aren't taking enough away to make it converge. And I have to be very careful here. I need one of the two to converge, the other to diverge. If they both diverge, it's possible that when I add these things together, they both go to infinity, but like maybe the addition of those two would go to something nice. So in particular, one goes to infinity, one goes to negative infinity. Maybe they go to 0, or maybe they go to some number in between when I add them together. So having two divergent sequences does not imply anything about the divergence or convergence of the sum or difference of those two sequences. So that sort of doesn't work out for us. But if I have one sum that is convergent, the other sum is divergent, then the sum or difference is still divergent. Okay. The last thing, if I have a positive integer m and I move where I start my sum. So instead of starting from 1, I start from m. Start from 15, start from 20, start from 200. Wherever I start, if the sum from 1 to infinity is divergent, so is the sum from m to infinity. Essentially, I cannot throw out enough terms to make this thing convergent. On the other side of it, I could essentially throw out an infinite number of these things and make it converge. But if I only throw out a finite number of things, I cannot make this thing converge, so if it's not convergent already. On the other hand, if I have the sum from 1 to infinity is convergent, well, then so is the sum from m to infinity, because the sum from m to infinity doesn't have as many terms. So certainly it's not going to like blow up because I've thrown out a finite number of things, right? And so here, they're either both convergent or both divergent. They cannot switch the convergence to divergence or divergence to convergence by throwing terms out at the beginning. Throwing an infinite number out at the end, that may happen that you get a convergent sequence from a divergent, but it's not going to diverge if you throw out an infinite number of things. It still might convert. It's still going to converge in that situation. Okay. So these rules, again, are a lot like the ones for integrals, and you'll use them like you do the ones for integrals. So most likely, you're not even going to be thinking about these rules as you're using them. You're just going to say, oh, I've got the sum of two things, and I'm doing the sum of that sum. Let's add each of those two things separately, then see if they converge or diverge, and then throw it back in. And then I have a constant times that thing. I ignore the constant, do the sum of the rest of it, and multiply by the constant at the end. Again, it's just like that integral. You're not going to sort of worry about the rule. You're just going to say, here, I'm going to use the rule and not name the rule. Yes. Cool. So that's it for now. And I will see you all on the next one, and enjoy your time. See ya.